Hi grade 11s, I'm John McBride.
And I'm Joyce Polko.
Today we're working through the practical on Newton's second law. Joyce will demonstrate the procedures and together we'll discuss points of interest as we work through this investigation.
Newton's second law states the acceleration of an object is in the direction of the net force. The acceleration is directly proportional to the net force and inversely proportional to its mass. The formula F net is equals to ma expresses the relationships between the net force, the mass of the object, and its acceleration.
The basic setup is a trolley on a track attached with a light, inextensible string to a weight that hangs over a pulley. When the trolley is released, the weight pulls the trolley down the track. The string must be light so it has almost no mass compared with the weights and the trolley. It must not stretch. We say it must be inextensible.
The force of the weight is exerted 100% on the trolley. There is no stretching of the string. Whenever something moves, it experiences kinetic friction or forces which resist its motion, such as air friction. This holds true for the motion of the trolley on the track. The trolley tends to slow down a little as it travels along the track.
We compensate for friction and resistive forces by raising the track slightly at one end until the trolley runs down the track at a constant speed. How are we measuring the speed of the trolley?
We'll use a ticker timer to measure the trolley's speed. Ticker timer is a gadget which has a vibrating point that makes marks on carbonized tape. We call the tape ticker tape. Here's the tape. If I scratch the tape with my nail, you can see a mark on the tape.
So if the pointer hits the tape hard at regular time intervals, while we pull it through the ticker timer, we can see dots on the tape. Let's try. Let's pull the tape through the ticker timer while the timer is switched on.
Right, the tape is fed under the pointer. We are ready to switch the machine on. Pull the tape at constant speed.
Here is the sample of the tape. The first part of the tape is rather messy, so we'll exclude that part. Here is a section of the tape where the dots are spaced at equal time intervals from each other. The tape was running through the machine at a constant rate.
We can even measure the speed of the tape. Measure the distance it moved in, say, 5 intervals of time and calculate the average speed as distance divided by time.
That raises another question. How many seconds are there between each vibration? Or let's phrase it another way. What is the frequency of the vibrations?
The frequency of vibration is the same as frequency of vibration of the Eskom main supply. In South Africa, electric power is supplied at a frequency of 50 Hz, 50 cycles per second. The period of vibration is equal to the inverse of its frequency. T equals 1 over F. T equals 1 over 50. Therefore, T equals 0.02 seconds.
We have marked off a section of 5 gaps and measured the distance the tape traveled during these 5 intervals. It traveled 19 millimeters in this time. The time taken is 5 times 0.02 seconds, which gives us 0.1 seconds. Distance traveled equals 19 millimeters, which equals 0.019 meters. The average speed equals distance divided by time, which equals 0.019 meters divided by 0.1 seconds, and that gives us an answer of 0.19 meters per second. The tape traveled at a constant velocity of 0.19 meters per second.
Our first task is to raise the track sufficiently for the trolley to run freely down the track at constant velocity while it pulls the ticker tape through the ticker timer. When we achieve this, we have set up a friction compensated track.
Let's check that the dots are evenly spaced on this tap. It looks like they're evenly spaced and the trolley is running down the track at constant velocity. I'm going to measure the different segments now. The first segment has a length of 20 millimeters, and the second segment also has a length of 20 millimeters. We have set up a friction compensated track. Why is it important that the track is friction compensated?
Newton's second law deals with the net force of the object. If there is friction acting on the object, the pulling force of the falling weight will be applied force, not the net force. We won't actually be able to record results for Newton's second law because we won't know the net force of the trolley.
So the friction compensated track allows us to use the pulling force of falling weights as the net force acting on the trolley. That's really cool. My next question is, how do we measure the acceleration of the trolley?
Acceleration is the rate of change of velocity. It is a change in velocity divided by the change in time. Acceleration is the final velocity minus the initial velocity divided by the time. We know how to measure the average velocity.
So all we have to do is measure the average velocity at two different time intervals to get the initial and final velocities. We also have to work out delta t. That is how much time passed while the velocity changed.
Here's a section of tape for the trolley accelerating uniformly on the track. I've marked off 3 consecutive segments of 5 gaps between the dots. I've measured the distance traveled in each time interval. Remember, each time interval takes 5 times 0.02 seconds, which is 0.1 seconds. Calculate the average initial and average final velocity.
Average velocity equals distance divided by time. The time is 0.1 seconds because we have used 5 gaps between the dots. The distance is 38 millimeters and must be converted to meters. So it is 0.038 meters. The velocity is 0.38 meters per second. And we can calculate the other 2 values of average velocity in the same way. Okay, done that. Now we calculate the change in velocity. The final velocity minus the initial velocity, that is v3 minus v1. But how long does it take to change the velocity?
Take a look at the tape. The average initial velocity occurred exactly halfway through the time interval. And the average final velocity occurred exactly halfway through the last time interval. So, the time gap is 1/2 plus 1 whole plus 1/2, which gives us 2 times 0.1 second. The time is 0.2 seconds. Let's complete the calculation.
Acceleration is equal to the change of velocity divided by delta t, or delta time. That is 0.48 meters per second divided by 0.2 seconds. The acceleration is 2.4 meters per second in the direction of the net force.
Another little point to make before we start taking results. The net force is equal to the weight of the slotted mesh pieces, which will hang over the pulley.
So we make a note of the total mass of the slotted mass hanger. This mass hanger has a mass of 5 grams, and the slotted mass piece has a mass of 5 grams. So the total mass is 10 grams. The net force equals the mass of the hanger times the acceleration due to gravity. We must convert the grams to kilograms. We divide 10 grams by 1,000 grams per kilogram and get 0.010 kilograms. So the net force in this case is 0.098 Newton. Now we are set up ready to begin taking measurements.
Very nearly. There's one last and very important point to note. The mass of the system must remain constant. This means that the mass of the trolley and the slotted mass pieces must remain constant.
Yes, we are working with acceleration and net force, so the total mass of the system must be kept constant while we change the net force and measure the acceleration.
There's a very neat way of doing this. The trolley carries all the mass pieces which are not hanging from the mass hanger. Take a look and see. In this way, the total mass of the accelerating system remains constant.
Okay, that's it. We are ready. Learners, you need a few minutes to read through the procedures in Part A, which we've already gone through with you, and Part B, which we're about to start doing. Get yourself a pen or a pencil so you can take down the results as we're going along. Hit the pause button now. Okay, folks, we're back on track. First, we'll set up the ticker timer with a new tape. Thanks, Joyce. Mark the tape as tape number 1. We feed the tape through the ticker timer and connect it to the trolley. There we go. We also make sure the trolley remains stationary on the track. We'll do this by holding the tape to keep it still. Next, we hang the mass piece, the slotted mass holder, and we hang it over the trolley connected to the string. This has a mass of 10 grams.
Record this mass in your table of results on the row for tape number 1. Don't forget that we need to keep the mass of the whole system constant. The 4 slotted mass pieces are on the trolley to keep the mass constant.
Now we need to act swiftly to get all of this running smoothly. Joyce, will you start the ticker timer and release the trolley?
Right, John, let's go. We need a ruler and a sharp pencil to mark the segment of the tape. Remember that we're counting 5 gaps between the dots, and we are marking off 3 consecutive segments of 5 dots. Learners, are you ready to record these results?
Segment 1 has a length of 39 millimeters. Segment 2 has a length of 41 millimeters. Segment 3 has a length of 44 millimeters. And that is the first set of readings done.
Just a hint here. The lines marking the segment of the tape must be exactly perpendicular to the length of the tape. Every millimeter counts in these readings. The pencil must be sharp, so you only draw a thin line on the tape.
We are ready to set up for the next set of values of net force on the trolley. We take a mass piece from the trolley and place it on the hanger. So let me do that. So there we go. We take the mass piece, put it on the hanger, connect the hanger over the pulley. The mass of the hanger is now 20 grams. We prepare a new length of tape and label it as tape 2. We feed it through the ticker timer and attach it to the trolley. And away we go.
Let's analyze tape 2. First, we must find a section of the tape where the dots are well defined and easy to see. Use the ruler, draw a line perpendicular to the tape. Count 5 gaps between the dots and make another line. Do this twice more until we have 3 consecutive segments. Now, we measure the length of each segment.
Results for tape 2. The accelerating mass is 20 grams. Segment 1, 54 millimeters. Segment 2, 61 millimeters. Segment 3, 66 millimeters.
Okay, tape 3 coming up. Here's the tape. Let's label it tape 3.
Now we need to move another mass piece onto the mass hanger. The accelerating mass is now 30 grams. Ready to roll, Joyce? Whoa!
And we analyze tape 3 just like we did for the other 2 tapes.
Results for tape 3. The accelerating mass is 30 grams. Segment 1, 62 millimeters. Segment 2, 68 millimeters. Segment 3, 79 millimeters.
We are setting up tape 4 now.
There are 3 mass pieces on the mass hanger. The accelerating mass is now 40 grams. And off she goes. And now we analyze tape 4. The accelerating mass is 40 grams. Segment 1, 86 millimeters. Segment 2, 98 millimeters. Segment 3, 109 millimeters.
The last round of the trolley is coming up.
We're taking 5 sets of measurements so that we can confirm a trend in the variation of acceleration with net force. If we only take 3 measurements, we have less data available to us. If we had time to take 10 readings, we would do even more certainty and have more reliability of our results. 5 sets of results are sufficient for our purpose. So we're going to move the last mass piece from the trolley onto the mass hanger. We've prepared a new tape and we're ready to go for the last time. We analyzed the last tape. Here are the results for tape number 5. The accelerating mass is 50 grams. Segment 1, 90,5 millimeters. Segment 2, 105 millimeters. Segment 3, 118 millimeters.
Right now, learners, you should have taken down these results on your worksheet. There are a number of questions for you to answer, such as naming the independent and dependent variables. You must also name the variables which remained fixed during this experiment. We will leave you to complete the worksheet for Part B before we begin demonstrating Part C of this practical investigation. Press the pause button until you are ready to start Part C.
Part C investigates the relationship between acceleration and mass, while the net force remains constant. In this experiment, we ask you to write down the method, but we don't need you to explain everything in detail again. The details have been included in Part B. So for instance, you can say, prepare a new length of ticker tape, thread the ticker tape through the ticker timer and attach it to the trolley. You don't have to explain how to measure the length of the tape as we did in Part B.
Now, we won't give the game away by showing you the method here. What we have done is to give you the results of an experiment so that you can analyze these and come to your conclusions. We will leave this work up to you.